So good day to everyone. Today we discuss about linear independence versus linear dependence. So to start off the discussion, let's try to define what a linearly independent set is. So suppose we have um, a finite set of non-zero vectors, capital S, consisting of the vectors v1, v2, all the way to vn. A linear combination of these vectors is expressible as basically the sum of the multiples of these vectors. So it's going to be C1 times V1 plus C2 times V2 all the way to Cn times Vn. Now, of all the linear combinations of the vectors in the set S that can be formed, we are in particular interested in that one which is equal to the zero vector. And we all know that the zero vector is just the vector whose components are all equal to zero. Okay. If it turns out that um, after solving for the C values, they are all equal to they are all equal to zero, then we say that the set S is a linearly independent set. So let us try to write that down. If if C1 is equal to C2 all the way to Cn are all equal to zero, then the set S is a linearly independent set. So to give a concrete example of this, let's try to consider the set S consisting of the vectors uh, 1, 0, 1, 1, 1, 0, and 0, 1, 1. And what we want to do is consider the equation, which is C1 times 101 plus C2 times 110 plus C3 times 011 being equal to the zero vector. Okay, and solving for the coefficients C1, C2, and C3. Now, incidentally, to solve for the C values, we will have to combine the three vectors on the left-hand side of the equation into a single one. And so this gives us C1 plus C2 for the first component, C2 plus C3 second, and C1 plus C3 in the last component. And this is supposed to be equal to the zero vector. In turn, this gives rise to a system of equations where the equations are C1 plus C2 equal to 0, C2 plus C3 is equal to 0, and C1 plus C3 being equal to 0. If we use the second equation, C2 plus C3 being equal to 0, then we get the following equation, which is C2 is equal to minus C3. And what we will do now is to um, put in C2 equals minus C3 into the first equation. So C1 plus minus C3 is equal to 0. And so this basically tells us that C1 is equal to C3. And then we substitute this into the third equation, which gives us C3 plus C3 equal to 0, or 2C3 is equal to 0, and from which we get C3 is equal to 0. C3 being equal to 0 and its equality to C1 implies that C1 is equal to 0, and um, C2 being equal to negative C3 implies that also C2 is equal to 0. So this implies then that C1 is equal to C2 is equal to C3, and all of them are equal to 0. And so therefore, we conclude that S is a linearly independent set. Now, just a brief comment. Um, the most important consequence of a set being linearly independent is that it basically means that none of its vectors can be expressed in terms of a linear combination of the other vectors. So this actually motivates the use of the word independent in the phrase linearly independent. So if we say that a set S is linearly independent, then none of its vectors basically depends on any of the other remaining vectors. So with that said, we now go to uh, the opposite concept of linearly independent set, which is a linearly dependent set. So when is a set linearly dependent? Okay, so again, we start off with a finite set of uh, non-zero vectors, v1, v2, all the way to vn, and then still consider the linear combination of these vectors. So we still have c1, v1 plus c2, v2 plus etc. all the way to cn, vn. We are still interested in that particular linear combination which is equal to the zero vector. Okay, but in the process of solving for the c values, if not all of the c values are equal to 0, then we call the set S linearly dependent. All right, so how does the concept of linear dependence work? So let's give a concrete example. So this time, let's have the set S to consist of the vectors 1, 0, minus 2, 3, 1, 0, 7, 3, 4. Then we still form the linear combination of these three vectors. So C1 times 1, 0, minus 2 plus C2 times 3, 1, 0 plus C3 times 7, 3, 4, and equate it to the zero vector. This will give rise to, again, a set of, or a system of linear equations where the first equation will be equal to C1 plus 3C2 plus 7C3 equal to 0. For the second equation, we have C2 plus 3C3 equal to 0. And for the last one, we have minus 2C1 plus 4C3 equal to 0. Now, if we try to express C2 in terms of C3, we will get C2 is equal to minus 3C3. And if we try to express C1 in terms of C3, then from the third equation, we get basically 2C3 And if we use these two equations into the first, what we get is the following. So 2c3 plus 3 times minus 3c3 plus 7c3 equal to 0. If we try to simplify the left-hand side, then we get 0 times c3 is equal to 0. Since any number we multiply with 0 is equal to 0, then we are at liberty to use any non-zero value of C3, and the set of uh, any value for that C3 will basically satisfy the set of linear equations that we have. So C3 then is arbitrary, and from here we know that C2 will be equal to minus 3C3, and C1 will be equal to 2C3. So in particular, if C3 is equal to 1, for example, then we know that C2 will be equal to minus 3 and C1 will be equal to 2. So now we go back to our original, which is this, and substitute our values for the C values. So we get 2 times 1, 0 minus 2 plus minus 3 times 3, 1, 0 plus 1 times 734. And indeed, a quick check on the arithmetic gives us the outcome that the sum of these vectors will be equal to the 0 vector. And so since not all of the C values are equal to 0, in fact, none of them are equal to 0, then we say that the set S is linearly dependent. So the set S is linearly dependent. Now, analogous to the case where S is linearly independent, a set S is linearly dependent means that any one of its vectors can be expressed in terms of a linear combination of the other vectors. So in fact, um, because of this, S being linearly dependent means any vector in that set depends on the other uh, vectors that is or that are included in that set. So, and we end our discussion there, and thank you very much.